Alright, ladies and gentlemen, this class recording has started. So, yesterday, we spent the day talking about work and energy, and specifically mechanical energy. First, mechanical energy, definition. How do we describe mechanical energy? How do we define or describe mechanical energy? Sean, go ahead.
Energy associated with the motion and position of everyday objects.
Energy associated with the motion and position of everyday objects. That's fine. You can just read it. That's fine, okay? So, Sean, the fact that it's energy means what? How do we define energy in general?
The ability to do stuff or move and change.
Come on here. The ability to do stuff, the ability to move or change other objects, the ability to do damage, whatever it might be, right? And those are all basically the same thing, just different ways of stating the same thing. And Sean, you just told us, right, the energy associated with the motion position of everyday objects. And as we can see here up on the board, right, mechanical energy is composed of three kinds. It's the sum of three kinds of energy, that being kinetic energy and gravitational potential energy and elastic potential energy. All right? Good there. First type of energy we talked about yesterday was kinetic energy. Describe for me kinetic energy. Hopefully this one's pretty easy. What is kinetic energy? Back on. Energy of motion, right? By the fact that something is moving, it has the ability to move or change other things. The amount of kinetic energy an object has depends on two factors. What are those two factors that determine the amount of kinetic energy something has? Matt, go ahead. Mass and speed. Matt, how do those two factors affect the kinetic energy? You got somebody else to go with this one? All right, Julia, go ahead. Mass doubles the amount of kinetic energy if we do what to the mass? Okay, so if we double it, we refer to that as a direct relationship. That mass doubles, kinetic energy doubles. If we make the mass 3 times as big, how much kinetic energy will an object have? 3 times, all right? So, direct relationship, mass, and kinetic energy, all right? What about the velocity, though? Okay, go ahead. The velocity will increase the kinetic energy by 4 times if we do what to the velocity? If we double the velocity, the kinetic energy increases by a factor of 4. So mathematically, what are we doing to the velocity in that formula, Kate? It's not up on the board, but this is what we talked about yesterday. So, hold on. Let me do this. Putting those two factors together, we come up with a formula to represent the amount of kinetic energy something has based on its mass and speed. And that formula is? Ke equals 1/2 mv squared, where Ke represents the kinetic energy, m represents the mass, and v represents the velocity, right? So kinetic energy equals 1/2 mass velocity squared, right? And then Kate, you kind of just told us that if we double the velocity, that means that we end up with how much kinetic energy? 4 times. If we made triple the velocity, if we made it 3 times as fast, how much kinetic energy would we end up with? Doesn't have to be Kate, it can be anybody. If we make this velocity 3 times as fast, if we go from 1 meter per second to 3 meters per second, how much kinetic energy are we going to end up with? We went over this a little bit more in another class. We didn't go over it as much in this class. So, any ideas? If we triple the velocity, if we make it 3 times as fast? Nope. 9 times, right? Jack, what do we have to do to velocity in that formula? Square it, right? So if we go 3 times as fast, 9 times the kinetic energy, because we have to go 3 squared. Okay? Good there? All right. I will preface the first part of class here with this. 1, we're going to do some example problems in class. And I kind of want to lead you through them because it's the first day we're doing it, and I want to make sure that we're addressing all the parts. If what we're doing here seems easy, great. Then you got this part down, no problem, right? And going forward, things should be a little bit easier for you, right? But if you need a little bit of help, that's why I want to do this, okay? So, I would like you to open your book, if you would please, to page 859. 859. And like I said, you don't all have to have a book out. If you want to share with the person next to you, that's fine, because we're just going to kind of use it to do the problems. So page 859. Be careful, Hannah. Be careful. Especially, Hannah, especially being this far back in the book. Just be careful. All right. So, on page 859, I want to look at question number 121. Now, one, I don't have an electronic copy of this book, so I can't show you the problem up here on the board. I apologize. Second, I don't have an Elmo either, so I can't even show you up here. So anyway, we're just going to have to talk. I'll try to write up on the board, make sure that you know like where we are and what problem we're doing. But if you're ever, if you're lost or whatever it is, then make sure you raise your hand, okay? Second thing, while we're going through this, all right, I really, really, really want you to stop me if you don't understand something that I'm doing. Because these calculations that we're doing today, these are, in the grand scheme of things, some pretty simple calculations, some pretty basic calculations. So if we're not understanding these, we got to understand these first before we can do the next ones, okay? So if you're not sure about something, raise your hand. Don't be a chicken, just raise your hand and say I don't understand, okay? Got it? All right. So, on page 859, number 121, it says, a sprinter runs with a forward velocity of 10.9 meters per second. If the sprinter has a mass of 72.5 kilograms, what is the sprinter's kinetic energy? So, Kate, you just told us that we have a formula that relates all the factors that influence kinetic energy, and that formula is? One half mv squared, all right? So, in this case, it wants to know the kinetic energy, so that's over here on the left-hand side of the equation by itself, so that's good. And then it gives us some things to work with. So, let's start plugging in those things that it gave us to work with. It told us that the mass of this sprinter was what? I can't see my book, so just tell me, what is the mass? Go ahead, Paula. So 72.5 kilograms. And then it told us that the sprinter runs with a velocity of, what is the velocity? 10.9. So 10.9 meters per second, but, like the formula says, we have to do what with that quantity? We have to square it. Okay? All right, so first, let's do the numbers, all right? So you go to your calculator. All right. So, is that what your calculator gave you? Maybe a couple more digits, depending on what calculator you have. Good there? I'll put you guys here because I don't need this much anymore. All right, so there's our number, okay? Now, let's do units. First, this is all just multiplication, so we can just mash them all together. Except here, right, with the velocity, that meters per second is inside the parentheses, so if we square the 10.9, we also have to square the units as well. So we've got kilograms here, but then we have, if we square meters per second, what do we end up with? If we square meters over seconds, we end up with, anybody? Anybody? That's what we're doing, right? Meters per second times meters per second. So what do we end up with units-wise? Meters squared over seconds squared. which is different than what you said, Tyler. So we'll talk about that in a little bit, actually. Okay. So meters squared over seconds squared. Okay? Good there? All right. A couple of things we have to do to finish this problem off. First, this conglomeration of base units, right? I've mentioned that to you twice already. That combination of base units we represent with what? Joules, right? So our unit for this problem is going to be capital J, right, representing joules, okay? But is that the number we should write down? Last unit, we learned about what? Significant digits, right? So here, we're multiplying and dividing. When we multiply, well, we're multiplying specifically, right? But when we multiply, our answer has to have how many significant digits? In general. As much as the least number of significant digits, right? Julia, how many significant digits in this number? How many significant digits in this number? So our answer should have 3, right? So, right, this one's significant. This one's significant. I wish I would have used a different color than that. But, all right, whatever. And then this one's significant as well, but the next place is a 6. So what should we do with that 0? We got to round it, right? So then our answer ends up being 431, but then we got to put the 0 on the end, right? You can't just drop that 0 because that's a place that is holding, okay? Is the 0 significant? Without the decimal, no. So our answer has 3 significant digits. Good there? All right, next question. Page 859 once again, but I would like to look at question number 122. So question number 122 says, a car having a mass of 654 kilograms has a kinetic energy of 73.4 kilojoules. What is the car's speed? Okay? Now, the way I'm going to do this problem is not necessarily how you have to do it. If you get to the answer another way, perfectly fine. I don't care. All right? But we just learned that the kinetic energy of an object determined by its mass and its velocity, and this is the relationship and how those two things come together. But in this problem, what are they asking us to solve for? They're asking us to solve for the velocity. Right now, velocity isn't by itself in this equation, right? So we got two choices. One, we can rearrange the letters before we put any numbers in, get velocity by itself, and then substitute in numbers at the end. Or we can put numbers in right now and then solve for velocity. I'm going to choose to do the first method. I'm going to rearrange the letters first, then plug numbers in at the end. So we have to get v by itself. What's the first thing we should do in order to get v by itself in this equation? What's the first step you would do if we had to rearrange this equation to get v by itself? Think back to those algebra skills, right? Julia, what would you do first? Okay, let's go make that two separate steps, right? Okay, so Julia says dividing by half. Dividing by half is the same as doing what, Julia? Not dividing by 2. Multiplying by 2, right? So let's multiply this side of the equation by 2, right? And that cancels out this 2. But if we multiply one side of the equation by 2, we got to multiply the other side of the equation by 2. So that leaves us then with 2ke equals mv squared. All right? And then, next thing we probably should do, divide by m, right? So we divide this side by m, that cancels out our m's here, but if we divide one side by m, we got to divide the other side by m, so we end up with 2ke equals, or divided by m, equals v squared. But, what do we really want to know in this problem? V, but we know, or the way the equation is set up, it's equal to v squared. So, Grace, what are we going to do last? Take the square root of both sides, right? And So we take the square root here, we take the square root here, and we end up with V equals the square root of 2ke over m. Okay? Good there? Everyone see how we got that? So, just algebra, right? Rearranging that equation, making sure we do the same thing to both sides of the equation so that we get what we're looking for by itself. Okay? Now, we can start plugging numbers in. Okay? So, square root of 2, and it told us the kinetic energy in the formula, right? Except, what unit did they give us the kinetic energy in? Kilojoules. But we really probably should have it in what unit, someone? Joules, right? Do we remember the conversion for kilo to... Anybody? The conversion for kilo something to somethings? There's 1,000 meters in a kilometer, right? So there's 1,000 joules in a kilojoule, okay? So we would take our 73.4 and multiply that by 1,000, or if you do the little King Henry died thing or whatever that, I don't know, right? Move the decimal point 3 places. So that would be 73,400 joules. And then, I believe they gave us the mass of this, what is this, car, right? 654 kilograms, right? And that equals V. Right? So now go ahead, plug things into your calculator, right? Okay, good. Well, let's talk about that, Kate. So, I don't really care as long as you round the correct, before the square root, take the square root first, then we'll round that answer at the end. Because the square root, being a mathematical operation, isn't going to change the number of significant digits in our answer. Does that make sense? Yeah. Okay. Does your calculator have the button that you can just press it to take the square root, or do you have to type it in again? Yeah, that stinks. There should be a way on your calculator that you can tell your calculator to take the square root of whatever answer you got on the last problem. Okay? It's probably a second function. I'll take a look. I'll take a look at it later if you want me to. Okay. So yeah, if you can avoid rounding before you take the square root, that would be better because you're you're mathematically taking the square root. Although, Kate, if you take it out like 6 or 7 decimal places, that your final answer isn't really going to be any different. Okay. But there should be a way that you can tell your calculator to take the square root of whatever answer it got from the previous problem, and then you won't have to type the number in again. Okay. All right. This is what my calculator gave me. Okay. First, even though I won't show you necessarily, if we're solving for the speed of this object, what should our unit be on this answer? What unit do we measure speed in? If you can't remember, look at the previous problem and they gave you a speed. What unit is it in? Meters per second, right? So meters over seconds, okay? All right, good there? And then, last step, right? Significant digit rounding. How many significant digits in 73,400? 3. How many in 654? 3, so our answer should have 3. All right, so I'm going to use a different color highlighter than the one I did last time. All right, this is significant, this is significant, this is significant, but just after the 9, we see that there's an 8. So what do we have to do to our 9? Round it up, but it's a 9, right? So we're going to round to 15.0. Is the point 0 important? Yes, got to be there. All right, good there. Okay. Yesterday, we continued our discussion about mechanical energy and shifted the focus from kinetic energy to potential energy. How did we describe potential energy? Or how did I describe potential energy to you? What is potential energy? Matt, go ahead. Energy that involves the position or location of an object. So kinetic energy is energy based on what it's doing. Potential energy is energy based on where it is. Does it have the ability to do damage to something else or to cause a change in something else because of where it's located? The one type of potential energy that we talked a little bit more specifically about was gravitational potential energy. And gravitational potential energy depends on location relative to what? Julia, go ahead. A source of gravity. Usually that source of gravity for us, Julia, is what? The Earth, right? So we're worried about where is this object located relative to the Earth. And we said that the amount of gravitational potential energy something has depends on 3 factors. What are those 3 factors that determine the amount of gravitational potential energy something has? What are the 3 things? Andrew, go ahead. Mass, height, the acceleration of gravity, which yesterday we talked about was like summarizing gravity's effect on an object at that location. And so we bring those all together, and the gravitational potential energy of an object is equal to m times g times h. Good? All right. On page 858 this time, so page 858, let's take a look at question number 116. So page 858, number 116. It says, a pear is hanging from a pear tree. Suppose that's better than if it was hanging from an orange tree or an apple tree or something like that, right? The pear is 3.5 meters above the ground and has a mass of 0.14 kilograms. What is the pear's gravitational potential energy? All right? Andrew, you just told us that the gravitational potential energy of an object is determined by 3 factors, right? Those 3 factors are? Height, mass, and the acceleration of gravity. We usually don't write them in that order, although it really doesn't matter because it's multiplication. It doesn't matter what order you write them, but usually we'll see it like this. Okay? All right, so let's start plugging in things that we know. They told us that the mass of this pear was 0.14 kilograms. Great. Know what it is? Yeah. And then they told us that the pear was 3.5 meters off the ground. Okay? So the last factor, this lowercase g, said was the acceleration of gravity, or summarizing gravity's effect on an object at that location. Here on Earth, that number is 9.81 meters over seconds squared, which is the unit for acceleration. Anytime we do a problem where an object is here close to the Earth, the value for g is 9.81. If we go to a different location that has a different gravity, like the moon, that number changes. On the moon, the acceleration of gravity is only about 1.6 meters per second squared. So if we wanted to figure out the potential energy of this pear on the moon, we would plug in 1.6. But we're not on the moon, so we keep it with this. Okay? Good there? All right. Anytime we do a problem here on Earth, that's the value for G. So, you plug that into your calculator, right? 0.14 times 9.81 times 3.5. You end up with that as far as the number goes, right? Units. Multiplication. So we're just mashing all these units together, right? So, kilograms times meters over seconds squared times meters. Right? When you multiply all those units together, what do you end up with? Kilograms times meters squared over seconds squared, which, Kate, we know is abbreviated with. That's the combination of units that we represent with joules, right? Should it be the same? Kate says yes. Is she right? Because what is it? We're calculating here the what? The gravitational potential energy. All energy is measured in joules, right? So, our final unit is going to be joules, okay? But, significant digits, right? How many sig digs in 0.14? 2, 3.5, 9.81, 3, so our answer should have 2. Good there? All right. Next thing I would like you to do, on page 859, I would like you to do question number 119. I am not going to walk you through this one step by step. I will do it up here on the board without talking about it, so you can check your answer once you get done, but I'm not going to walk you through it. So go ahead, work on it on your own, and I'll get you the answer up here on the board. Super non. We buy the super non-absorbent kind of tissues here. So. You might as well just. Quite honestly, you might as well just use paper. I mean, that's about the same quality. So. All right. How's that? Do we need a couple more seconds? Questions about that one? All right. Yesterday, towards the end of class, we talked about work. And what was our description of work? How do we describe work? Julia, go ahead. The transfer of energy between objects. In order to transfer energy between objects, we had two requirements. What are the two things that were required in order for energy to be transferred between an object? Okay, go ahead. Good. So the energy is going to change, and we do that by applying a force. And what has to happen when we apply that force? An object has to move. Right? So, and we summarize those effects with the equation work equals F times D. Okay? So, next thing I want us to do, now, I found out this earlier today that actually there are, even though these are the same copyright date of the book, there are apparently two printings of the book. We're going to do question number 101. Some of you may find question number 101 at the top of page 158, but some of you might find it at the bottom of page 857. So, find question number 101 wherever it might be. So, it was really intense when I said page 857, number 101, because that's where mine is, and people were like, it's on 858. And I was like, no, it's not, it's on 857. Yeah. So, not that I was just like, whoa. So, all right. So, mine is on page 857, so I'm going to write page 857, but yours might be on page 858. 101. So it says, a car breaks down 2.1 meters from the shoulder of the road. 1.99 times 10 to the third newtons of force is used to push the car off the road. How much work has been done on the car? So, we just learned that the amount of work that's done on an object is equal to or determined by two factors. And what are those two factors? Force and distance, right? So all we're doing is just multiplying force times distance. Okay? First, did they give us a force? They did. They gave it to us in scientific notation, which is fine. Or, because that one's kind of a simple scientific notation, we can change it back into regular decimal notation. I'm going to do that. So 1.99 times 10 to the third newtons is the same as 1990 newtons. Okay? And it tells us that we moved this car 2.1 meters. Okay? Now, before we go any further, I want to do something for you. Okay? Newtons, this capital letter N right here, right? We haven't used that notation in class yet. You might be familiar what it is from somewhere in the past, okay? It's a unit to measure force, but it is also a derived unit representing a combination of base units. The Newton is equal to kilograms times meters over seconds squared. So very similar to the unit for joules, but not quite the same. So we represent it differently. But whenever Newton shows up in a problem, we can substitute in this combination of base units to help us figure out the unit of the final answer. So I'm going to change this to 1990 kilograms times meters over seconds squared times 2.1 meters. Everyone see what I did there? You okay with that? Okay. Run it through the calculator. All right. 1990 times 2.1. We end up with 4179. Right? But then if we look at our units, right? Kilograms times meters over second squared times meters. What are we going to end up with on the top there? Julie, go ahead. Kilograms times meters squared over second squared, which is our combination represented by joules, right? So the answer to this problem is going to be in joules. How many sig digs should our answer have? 2. So we're going to round this to 4,200. Decimal point or no decimal point? No decimal point. So 4,200 joules. Question. Is it okay that work and energy have the same units? Minus shaking your head yes. Just because if it's not, then we have a problem with this? Or okay. What was our definition of work? How do we define or describe work? Andrew, go ahead. The transfer of energy between objects. So work really is energy. It's just energy going from this place to that place. So if it's energy, what unit should it have? It should have a unit of joules. So work and energy are going to have the same unit. Work is just energy that flows from one place to another. Okay? Good there. All right. For tonight, here's what I would like you to do. Tonight, September 18th, homework is a bunch more practice problems calculating kinetic energy, potential energy, work, etc., etc., etc. Okay? Remember, I'm not collecting these. I want you to do as many as you feel comfortable doing. Make sure you round properly. Make sure you end up with the correct units. All right? This kind of stuff will show up on your quiz. But your quiz is going to get pushed from Friday to Monday because that sheet that I asked you to get out at the beginning of class that said work and energy concepts, those things will also be on your quiz on Monday. We haven't talked about those just yet. So we're going to push the quiz to Monday. But for tonight, these practice problems. Questions? You okay there? All right then. Have a good evening, everybody. I will see you guys tomorrow.